Hello everyone. So today we're going to do 14.7, which is power series solution. So in 14.7, what we're going to try to do is very similar to what 14.6 tried to do, is to come up with a solution using power series. The difference is in 4.6, what we try to do is try to form the Taylor series of a solution. While in 14.7, what we're going to try to do is we're going to try to assume that the solution is a power series, or it has a power, the differential equation that we're dealing with has a power series solution, and we're going to try to actually form this power series by finding its coefficient. So you might not remember what understand what that means yet, but once we get through start talk about it, hopefully it will make more sense, especially if you remember some of the things that you learned back in basic calculus. So we call from basic calculus, a power series is simply just basically is a polynomial of x, is a sum of powers of x, basically. So a power series of x is just a series of the powers of x in the form of summation n from 0 to infinity a sub n x to n, which is just a sub 0 plus a sub 1x plus a sub 2x squared plus dot 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 plus a sub n x to n plus dot dot dot. And an example of a power series would be Taylor series. So in a Taylor series, we simply define a sub n to be equal to f to the nth derivative of 0, or actually, maybe to be fair, x sub, well, actually 0 would be fine because it's a power series, so it didn't get moved. So technically, I guess I probably should call it Macron series, but it's okay. Okay. So notice that the way to define a power series is actually by defining its coefficient. So note, to define a power series, we need to basically define all its coefficients, which is in this case the set of a sub 0, a sub 1, dot dot dot, or a sub 2, dot 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 to forever. So that's what we've been trying to do, but of course in 14.6 we realize that some of these coefficients doesn't form a pattern that we can use, or rather the pattern just hard to notice, and therefore we only try to attempt to generate a certain number of terms, and then if we do need more terms to be more accurate for our answer, we just generate more terms recursively. So what we're going to try to do in 14.7 is to try to see if we can actually come up with a way to actually generate these coefficients so that we can actually form the power series properly. Of course, in some cases, we'll run into some nice and simple example where we can easily see what the coefficients are. In some other cases, it will take some creativity to try to figure it out. So what I want to do is to simply show you how to do that. So let's start with a simple differential equation. So to help you understand how to do this, we'll start with a very easy example first. So here's our example. we're going to go ahead and solve this differential equation. Okay, we're going to try to solve this differential equation using a power series solution. Okay, now before we start, I want everyone to look at this equation and tell me what the solution to the differential equation is. And if you cannot tell me the solution to this differential equation in about 12 seconds, you really need to study and look back in your notes to try to figure out and remember some of this stuff. Okay, so give you 12 seconds. All right. So that's roughly about 12 seconds. You should now have an answer. If you don't have an answer, you really haven't been paying attention or learning some of the stuff that I'm showing you. Okay, show you what the answer is, and it will probably take me less than 12 seconds to write it out. So y prime plus y equal to 0, meaning it's d plus 1 of y equal to 0. That means the characteristic equation r plus 1. That means r is equal to negative 1. That means y will equal to c sub 0 e to negative 1x, or negative x. There you go. That's the solution right there. It took me less than 12 seconds to write that out. Okay? And if you didn't see that, you really haven't been learning or paying attention to some of this stuff and haven't remembered some of this stuff that I show you. Okay? This is a very basic differential equation. Now, obviously, if you see this equation, you're not going to use a power series solution. It takes 12 seconds to answer that question using characteristic roots. So why would we use power series solution? But as I say, I'm trying to give you a very simple example to illustrate the process. Okay? So how do we start if we were to use a power series solution? Well, the first thing we're going to do is we're going to let our solution be a power series. We're going to let y of x to be equal to some kind of power series and I'm going to use k as my index instead of n, because sometimes I like to use n as the top number for the index. So like it's k from 0 to n, so I want to avoid using n. So k seems like a good idea. I is okay, but I sometimes can get confusing when you write it too many of them. So I think k is a good index to use. So this is what we call a power series solution. So let y of x equal to summation k from 0 to infinity c sub k x to k. So this is what we refer to as a power series solution. So in order to actually generate this power series solution, what I'm trying to do is try to figure out what c sub k is. So we're going to try to see if we can actually find what we call a closed form of c sub k, meaning some way to define c sub k based on k itself. Notice that there's something that we cannot do in 14.6. When we do the Taylor series, sometimes they form a nice pattern, but sometimes they don't. And when they don't, we really don't have any way to generate the coefficient other than to generate them recursively one after another one. In some cases, some of them become 0, and then we have to skip them and move on. So hopefully we can bypass that issue. So how do we go about doing this? Well, simple. Since this is a first degree differential equation, I do need to know what y prime is. And if I define y to be this power series, then I can basically define y prime to be the derivative of y. That means is the derivative of this power series. Now, it's the first time seeing this, I want to go through the process. So summation, because the differential operator d over dx, or derivative or differentiation, is linear, I can actually distribute this inside our summation. And since c sub k is a constant, I'm actually going to pull that out of the differentiation also, and therefore I'm actually just differentiating x to the k. So that means I can actually rewrite this into this. First, by moving the differentiation into our summation. Because remember, when you take a derivative of a sum of a whole bunch of things, I just basically add up the derivative of each of the terms that we have. And since c sub k is a constant, I'm going to pull that out of the differentiation, but not out of the summation, of course. And so what does that equal to? Well, we can just simply differentiate x to k like we normally would do. And here's something interesting that I want to show you. Is our index no longer start with 0, but instead start with 1. The reason, because our first term c sub 0 actually go away in this expression. So therefore, we should not have a c sub 0 term anymore. Not to mention that this, if I start k with 0, it doesn't work because then I will have k to negative 1, which is not what a power series is. A power series, if we talk about powers of x, a positive, non-negative integers power of x. So therefore, this index will have to start with 1. But of course, that is the problem because I don't like my index to start with 1. So how do we fix that? What I'm going to have to do is re-index. So now what I'm going to try to do is I'm going to try to re-index this power series. So how do I actually do that? So I'll show you how that works out. So if I were to write out this whole thing, the c sub 0 term go away because the derivative of constant is 0. Therefore, I don't have a k equal to 0 term, so I have k equal to 1 term. So if I start, it will just be c sub 1, k, which is 1, x to the 1 minus 1, which is 0, plus c sub 2 times 2 times x to the first. And I'm kind of running out of room. I'm going to just do it half a line. Well, maybe I do it here. C sub 3 times 3, k x to the second. And so on and so forth. So now what I can do is just simply re-index it. And why do I want to re-index it? Because I want to re-index it so they become a power series like the solution that we have, which would mean that we have to start with 0. So if I look at this right here, notice that if I do use 0 as a first power, that would just mean that the number in front of it become 0 plus 1, and the c will be sub 0 plus 1. So therefore, I can actually change this back into starting from 0, but re-indexing c sub k to c sub k plus 1. This expression right here, when I plug in 0, I will still get the first term c sub 1 times k to 0. If I put in 1 for k, I would have c sub 2 times x to the first. If I plug in 2, I get c sub 2 plus 1, which is 3, times 2 plus 1, which is 3, and then k to x to the second. So notice that by re-indexing, I can generate the first 3 terms with no problem. And now I actually start with 0. If you think about it, all it does is the following. Because I changed the k number to start at 0, meaning 1 less, because I go from 1 to 0, which I have to minus 1 to do that. I have to balance that change of minus 1 in my index, starting index, by changing all the instance of k inside my expression to k plus 1. That's all that is. If you find that to be too confusing, or you don't really follow the logic, which is okay, that happens, how about just memorize this is what y prime is if you let y equal to a power series solution, which is what you're always going to do on every single problem. So you can simply just memorize y prime, and then voila, you have it. Because you have to 1 by y anyway, so, might as well. So now, how does that help us? So this is how. Now that I have a power series for y, and a power series for y prime, I can now form my equation. So y prime plus y equal to 0 would basically tell me is the summation k from 0 to infinity c sub k x to k plus summation k from 0 to infinity c sub k plus 1, k plus 1, x to k equal to 0. Here's the important part that we want to achieve. Is inside the formula, we have a correspondent of x to the k. Because they are not the same, it makes it a lot harder for me to combine these two summations together. Another issue that you want to look at, or you might run into, is where the index begin. These two doesn't have to be the same, and if they're not the same, there's an easy way to fix that. The key is to set up so that the both sigma notation have x to the k inside. Because if you don't have that, you would not be able to combine the two summation together. So that's the key. So that's what you want to write down to remind yourself. Whatever you do, that's what you want to actually achieve, is to set up the summation so that you have x to the k, or whatever x to whatever power. It has to be the same. So meaning that if you have the first one is x to the k plus 1, but the second summation also have x to the k plus 1, then you're still okay. Even though I don't know why would you do that, because you probably adjust the starting index so they can change it to x to the k. But if that's what you prefer, you can. You just make the math more confusing. So the key is to set up so that your summation, your multiple summation, would have x to the k as the term inside. Now, because that is the case, now I can actually combine these two summation together into one summation. And if you don't believe me that we can do that, you can easily write out the summation, write out the first 4 terms of the first summation and the first 4 terms of the second summation, and you found that you can actually combine them together. Okay? You know what? As a matter of fact, you know what? See, as our first example, let me just do that. Let me just show you this. Okay? If I write out the first 4 terms of this summation, there will just be c sub 0 x to 0 plus c sub 1 x to first plus c sub 2 x squared plus c sub 3 x to the third plus dot dot dot. If I take the second summation and write out the first 4 terms, I will have c sub 1 times 1 x to 0 plus c sub 2 times 2 x to the first plus c sub 3 times 3 x to the second. And I can't run out of room, I'm going to put a second line. C sub 4 x to the third plus times 4 x to the third plus dot dot dot. And so if I combine these two summations together, I would basically just have this. C sub 0 plus C sub 1, x sub 0, which is 1, but I still want to write x sub 0, so you can see that's a 0 power term, plus C sub 1 plus 2 C sub 2, x to the first, plus C sub 2 plus 3 C sub 3, x to the second, plus c sub 3 plus 4 c sub 4 x to the third plus dot dot dot. So that would be what this summation turned into. So now you should hopefully notice that there is a pattern to this coefficient info of x sub 0, x sub 1, x sub 2, x sub 3, and on. And that pattern is pretty simple. It's literally just this. C sub k plus c sub k plus 1 times k plus 1. And you can definitely check that out to see that that's exactly what it is. If you're plugging 0, you have c sub 0 plus c sub 1 times 1. If you're plugging k equal to 1, you have c sub 1 plus c sub 2 times 2. And then you're plugging 2, you have c sub 2 plus c sub 3 times 3, so on and so forth. And we'll say this is equal to 0 because that's what the formula suggests. So now here comes an important part. Here comes the important part. If you have a power series on the left side is equal to a power series on the right side, then the only way for these two power series to be equal to each other is when all the corresponding coefficients are the same. And I know what you're thinking. Wait a minute, we don't have a power series on the right side. Of course we do. See, 0, technically speaking, is 0 times x sub 0 plus 0 times x sub 1 plus 0 times x sub 2 plus 0 times x sub 3, so on and so forth. It is a power series. And in this power series, every single coefficient is simply 0. And on the left side, we also have a power series where each of the individual coefficient is defined by this expression. While on the right side here, every single c sub k is 0 for every single one of them. Or actually, you know what? I'm going to call it a sub k. And this whole thing is what we refer to as a sub k. Because one collective coefficient. So therefore, meaning it suggests that this expression right here should equal to 0. That is how we go solve for c sub k. What we have right here is a recursive formula. A recursive formula. So this recursive formula would now allow us to generate each c sub k and hopefully create some kind of way for me to form a pattern. Okay, so how do I do that? Well, I'm going to try to rewrite it. I did say it's a recursive formula, but it doesn't look like a recursive formula until I put it into the correct form. And that would be this. So now we have a formula. So now what we're going to try to do is now try to start with our coefficients and see if we can generate all of the coefficient in some way. So the way to do that is to just go through the list. We're going to start with k equal to 0. Then what we have will be just this c sub 0 term. That's our first starting coefficient. When k is equal to 1, well, actually, maybe I'll do this so that I can help you understand better. So that referred to as the constant term, which is the x to 0 term, and we're gonna have just c sub 0 as our first coefficient. What happened to k sub k equal to 1? That would mean the x term, because x to the first power, and that would be equal to negative c sub 0 over 2 over 1. Oh, actually, I'm sorry. This is our beginning term, and here is where k equal to 0. That's why. K equals 0. Then we have our constant term. So when k equal to 0, okay, maybe I should write it better. Hopefully that makes more sense. Okay, we're going to start with our constant term. Yeah, this way probably better. Which is going to be z sub 0. Let's start with our k term. So k term, we're going to need c sub 1. So c sub 1 will actually equal to negative c sub 0 over 1. Why? Because in this scenario right here, we actually have c equal to 0 plus 1, would that equal to negative c sub 0 over 0 plus 1. That's basically what the formula you see right there. That would generate c sub 1 term, which is basically for the x term. Now I can do the x squared term. That means I need c sub 2. So c sub 2 would actually be equal to negative c sub 1 over 2. Why? Once again, that would be because c sub 1 plus 1 equal to negative c sub 1 over 1 plus 1. So that allows me to generate the 2 term. Notice that this 2 matches the exponent. That's how that works. Okay. And what happened to this expression? Well, this expression is saying negative c1 times 2. But we do know what c1 is, so I can actually change that. So I'm going to change that into this. become negative of C1, which is C sub 0 over 2. Oh wait, double negative, I'm sorry. So therefore, it just becomes C sub 0 over 2. So that's our C sub 2 term. And now we can continue to do this until we get to more terms. So now, it should quickly, you should be able to get the hang of it. So x to the third terms will be where we need C sub 3. And C sub 3 would equal to negative C sub 2 over 3. There's a nice simple pattern going on. And that would just equal to negative C sub 0 over 2 times 3. And yes, some of you probably recognize a factorial is going, because this would actually be 1 times 2. And now it's 1 times 2 times 3. And what happened to x to the fourth term? That would require me to form C sub 4 term. And one of the important things that I need you to understand is that this C sub 4 is not really relating to this formula right here, but rather relate to our power series solution, where C sub 4 would generate the x to the fourth term, and C sub 3 would generate x to the 3 term, and so on and so forth. So that's basically what we try to write out. So here would be the coefficient that we need for our power series solution. So you should be able to take a wild guess as to what C sub 4 is. C sub 4 will actually be C sub 0 over 1 times 2 times 3 times 4. Or C sub 0 over 4 factorial. And if I continue this pattern, it shouldn't be too hard for you to figure out that x to the k term will generate C sub k. Actually, you know what? I'm not going to use that. I'm going to use the letter n. Will just equal to C sub 0 over n factorial, but it does alternate sign. So here you just have to figure out how does it alternate sign. So for 0 is positive, 1 is negative, 2 is positive, 3 is negative. So therefore I would say it's negative 1 to the n. So n is 0, then we're given positive number. So now that is now something that I can use to form my power series solution. You know what? Actually, I think I can use k. That's okay. I'm worried that you get confused, but technically speaking, I should use C sub k because that's how our solution, power series solution, is used. So I'm going to just follow along. So that would tell me that our power series solution, y, would actually equal to summation k from 0 to infinity, negative 1 to the k, C sub 0 over k factorial, x to the k. Now, that obviously is the same as this answer right there. How? Well, simple. Let's figure it out. I'm going to first pull out the C sub 0 from our summation. And notice that this whole thing will just turn into negative x to the k over k factorial. And this summation would just equal to e to the negative x. So therefore becomes C sub 0 e to the negative x. We arrive at the same exact answer, but they took about 20 minutes. But of course, remember what I just said, you're not going to use power series solution to solve a differential equation like this one, because this one you can do using characteristic roots and take you about 12 seconds to complete. All right. Unfortunately, my time kind of ran out. It's already 29 minutes. So I'm going to stop right here and continue to give you more examples. That's all we're going to do, is to learn how to kind of use this method to generate the power series solution for differential equation. And somehow try to collect and find a way to generate C sub k. So that's all we're going to do. I just need to show you more examples so that you can see what happened when you run into different scenario. All right. That's it, and I'll talk to you again in the next video. Okay, bye-bye.